Video I'll be talking about the use of step size control in Runge-Kutta methods. Okay, so we've talked about step doubling, and what step doubling did is it would calculate a single step of the Runge-Kutta method, and if that step was considered to be accurate enough, we'd move on to the next step. But if it wasn't considered accurate enough by some estimate of the error, we would halve the value of h and then repeat the step. If our accuracy requirements were exceeded, so if we found that our estimate of our error was much less than a given tolerance, we would double h. Okay, so that did a job, but it's not very efficient. The reason it's not very efficient is we only double or halve the step length. We don't make minor sort of subtle adjustments to the step length, and this is where adaptive step size control comes in. It makes small changes to h based on the accuracy of the current step. Okay, so the premise behind it is that you calculate the solution of a single step h using order p method and an order p+1 method, and then you estimate the error, which is known as EST, for the p+1 order solution. Okay, you do that by comparing the order p with the order p+1. Now, if that estimate of the error was much less than tol, and remember that tol is some small number known as the tolerance, usually something like 10 to the minus 4 or 10 to the minus 6. So if s was less than that small number, the step is considered successful. We proceed to the next step, and we also increase h. So we'll increase h based upon how accurate we consider that last step to be. If, however, our estimate of the error was greater than tolerance, so the step has failed because our solution isn't accurate enough for our purposes, we decrease h and then repeat the same step again. So the difference between adaptive step size control and step doubling is that adaptive step size control always changes the error, and when it does change the error, it makes slight adjustments. When it does adjust the step length h, it makes slight adjustments to it. Okay, so how do we change this the step length? Okay, so this is taken from the definition of big O h to the n. So if you need to know what that is, I suggest you look at the lecture notes or the previous videos. So the estimated error of using a step length is this. Okay, so it's some value c, we don't know what c is, it's some positive value, times the step length to the power p+1. Okay, so we need to ensure that if we have a new step length, that our new step length has an error which is the same as the tolerance. So that's what we're doing. So let's say that our current value h, the error was less than tolerance. What we're going to do is we want a new value of h where the error would equal the tolerance. So we're maximizing the efficiency in our method. So we're going to say that this is equal to c, which is again some positive number, times a new step length to the power p+1. So what we need is a ratio between the new step length and the current step length. So if we let r equal h new divided by h, and then what we do is we divide the right hand sides of both of these equations. So remember, the top one was equal to tol and the bottom one was equal to est. Okay, so that's our rp to the power p+1. Okay, and if we solve for r, we have our tolerance over our estimated error to the power 1 over p+1. Okay, so we know what the tolerance is because that's something we determine. So as I mentioned before, it's either 10 to the minus 4 or 10 to the minus 6 or a number in that kind of region. We've calculated our estimate of our error, and we know what p is because that's the order of our method. Okay. Now, so this going back, what we will do is this ratio, we simply multiply our current step length h by this ratio, and that will either increase or decrease h depending on whether est was greater than or less than tol. Now, for robustness, we don't want our h to change too much, because if you have large abrupt changes in h, you can affect the stability of the method. So what we do is we actually try and limit r so it never more than doubles our step length or never more than halves it. Okay, so there's that subtle changes, and to do that we make use of maximum and minimum functions. Okay, so if we're starting from the inside here, okay, so we have our value of r, which is tol over s to the power 1 over p plus 1. What we do is we multiply that by 0.9. Now this is a safety factor. This is to ensure that we're not ever going over what r should be, and therefore having a failed step at the next step of the algorithm. Okay, so here we've got a minimum value. So remember, this is the ratio r. So what we want is, we do not want our h to more than double over a single step. So we limit it to be 2. Okay, so it's either a minimum of 2 or a calculated version of r. So that means it's kind of got an upper limit of 2. And we also don't want to go any further than halving a step length over a given step. So therefore we have the maximum of a half and whatever the result of this minimum function is. Now the values of a half, 2 and 0.9, these are arbitrary. These are something that we can change, and they're regarded as what we in the trade we refer to as design parameters, but these tend to work quite well in most cases. Okay, so we have everything we need apart from this estimate of the error, this EST value here, and we estimate the error as using the difference between an order p solution and an order p plus 1 solution, and this gives rise to what we call embedded Runge-Kutta methods. Now, embedded Runge-Kutta methods are a single method which have an order p and an order p plus 1 solution built in. So for example, if we had a general form of a fifth order method, or a fifth order method requires 6 stages. Okay, so that's the general form. Okay, and we update our value yn plus 1 equals yn plus a weighted sum of our stage values. So that's a fifth order method. Now, using the same values of k1, k2, etc., we can calculate a fourth order method using those same values. So this is what we call an embedded method. So we have a fifth order method, but without recalculating k1 up to k6, we could also calculate a fourth order method. Okay, so notice we have additional values of b1, b2, which are denoted by the star, and also this is our fourth order formula is denoted by that star. Okay, now the Butcher tableau, if we want to represent an embedded method in a Butcher tableau, we simply include the b1 star, b2 star, etc. in a row underneath the b's. Okay, so this is a typical Butcher tableau for an embedded Runge-Kutta method. So you've got your c values, you've got your a values, and your b values as normal, and then you have your starred b values in the row underneath. And the estimate of the error is the difference between the order p plus 1 solution and the order p solution. Okay, so yn plus 1 star is the order p solution, yn plus 1 is the order p plus 1. Now, if we go back a slide, if I subtract these two, okay, so I'm going to subtract the two expressions for yn plus 1, this will eliminate yn, and we've just got the difference between the b1 and the b1 star multiplied by some k value. So instead of actually calculating what our order p and order p plus 1 solution is, we can actually subtract the bi minus bi star, multiply that by the stage value ki, and sum them all and times by h. This will give us the same error. So in other words, we don't need to calculate the actual step yn plus 1, because sometimes we want to repeat the step, so that's wasted effort if we're calculating yn plus 1. Okay, so here's the next few slides. I'm going to show you a few examples. So there are sort of only a few examples of embedded Runge-Kutta methods. Usually they're fifth order, or what we call order 4-5. So first one, or the earliest one, is Runge-Kutta-Fehlberg method, which is a fifth order method with an embedded fourth order formula. So you can see here these b values is the b values for the fifth order solution, and the ones below are the values for the fourth order solution. Now the MATLAB solver ODE45, the 4-5 refers to this fifth order with a fourth order embedded in it. So the ODE45 is actually a Runge-Kutta, embedded Runge-Kutta method. Another example is the Dorman-Prince method. Okay, so the Fehlberg method had 6 stages for a order 4-5. The Dorman-Prince has 7 stages for an order 4-5 method. Okay, and the final one, the most recent, is the Cash-Cart method, which again only has 6 stages.